Welcome to the production facility where some of the world's most impressive wind turbines come to life, Enercon's manufacturing operation. If you remember when wind power meant small windmills on farms, prepare to have your mind blown by the scale of modern renewable energy engineering. Enercon, a German company founded in 1984, pioneered the gearless direct-drive wind turbine design. What you're watching is the assembly of these technological marvels, and the numbers are staggering. These turbines can stand over 600 feet tall with rotor diameters exceeding 450 feet. That's taller than most skyscrapers folks our age watched being built. Let's start with the heart of the system, that massive generator you're seeing assembled. Unlike conventional turbines that use gearboxes, Enercon's ring generator directly connects to the rotor hub. This design eliminates thousands of moving parts, dramatically reducing maintenance and extending operational life. The generator ring contains hundreds of electromagnetic coils, each wound with precise copper wire thickness and turn count. These coils must be positioned within millimeter tolerances around the entire circumference. Watch the technicians installing these components. Every connection is tested multiple times, because once this generator is mounted 400 feet in the air, repairs become exponentially complex and expensive. The assembly process follows strict protocols developed over decades, quality control procedures that would make old-school craftsmen proud. Now observe the rotor hub manufacturing. This component must withstand forces exceeding 100 tons during operation while maintaining perfect balance. The hub is typically cast from ductile iron, then precision machined on massive CNC equipment. Each blade attachment point is machined to tolerances of less than 1 millimeter because even tiny imbalances at these rotational speeds create devastating vibrations. The nacelle, that's the housing that sits atop the tower, contains not just the generator but also sophisticated control systems, hydraulic units for blade pitch adjustment, and cooling systems. Modern Enercon turbines use integrated converter technology, converting the variable frequency AC from the generator into grid-compatible electricity right inside the nacelle. See those blade sections being prepared? Enercon blades are manufactured using advanced composite materials, glass and carbon fiber reinforced plastics. Each blade is built in precision molds, with multiple layers of fabric saturated with resin, then cured under controlled temperature and pressure. A single blade for their largest turbines can be 240 feet long and weigh over 30 tons. The tower sections you're seeing are rolled from high-strength steel plate using machines similar to the Heisler system we discussed earlier. Each section is welded, stress-relieved, and coated with multiple layers of corrosion protection, because these towers must survive decades of exposure to wind, rain, salt air, and temperature extremes. Final assembly involves lifting these components hundreds of feet into the air with specialized cranes. The precision required is remarkable. Aligning bolt patterns while managing tons of steel swaying in the wind takes skills that blend traditional rigging knowledge with modern engineering. What strikes me most is how this technology represents humanity's oldest power source, wind, harnessed with our most advanced manufacturing capabilities. It's progress that honors the past while building the future. Here's where the rubber meets the road in modern precision manufacturing, CNC lathe work. For those who remember manual lathes, this is both familiar and absolutely revolutionary. A CNC lathe spins the workpiece, while computer-controlled cutting tools shape it with incredible precision. This machine is working on what appears to be a steel shaft, and every movement is choreographed by programming down to thousandths of an inch. See that tool turret? It holds multiple cutting tools, turning tools, boring bars, threading tools, grooving tools, all indexed automatically. No more stopping to change tools manually like the old days. The machine selects the right tool, positions it precisely, and executes each operation in sequence. Modern CNC lathes use live tooling, meaning the turret itself can rotate tools for milling operations without removing the part from the chuck. That's how you get complex features like cross holes and flats on round parts, all in one setup. The coolant floods the cutting zone, washing away chips while keeping temperatures stable. Those gleaming spiral chips peeling off? That's the sign of proper cutting speed and feed rate, all calculated by the machine's controller. This technology produces everything from automotive components to medical implants, combining the timeless principles of lathe work with computer precision our predecessors could only dream about. Now here's something that really takes you back to the golden age of heavy industry. We're looking at oxy-fuel cutting, a technology that's been around since the early 1900s, but it's still the go-to method for cutting truly massive pieces of steel like this one. This solid steel block measures 1,000 by 1,000 by 200 millimeters, and weighs a staggering 940 kilograms. That's over 15,000 pounds. Cutting through something this substantial requires serious heat and precision. The oxy-fuel cutting process works on a beautifully simple principle that stood the test of time. The torch uses a mixture of pure oxygen and fuel gas, typically acetylene or propane. First, the operator preheats the steel's surface to its ignition temperature around 1800 degrees Fahrenheit. Then, a high-pressure stream of pure oxygen is directed at that glowing spot, creating a rapid oxidation reaction, essentially controlled burning that cuts right through the metal. What you're witnessing is the cutting oxygen stream traveling at supersonic speed, literally blowing molten steel and iron oxide out of the cut zone. That spectacular shower of sparks? That's the oxidized metal being expelled from the kerf, the gap created by the cut. For steel this thick, the torch moves deliberately slow, perhaps just a few inches per minute, ensuring complete penetration. The operator must maintain precise torch angle and distance from the work surface, skills that take years to master. Despite all our modern laser and plasma technologies, oxy-fuel cutting remains unbeatable for steel over 6 inches thick. Sometimes, the old ways really are the best ways. Back in the day, making molds for aircraft parts meant weeks of painstaking handwork. Today, we're watching something that would have seemed like pure science fiction to the craftsmen of yesteryear. This is the Datron M8 Cube CNC milling machine, and it's creating a fiber mold for a quadcopter drone from a solid block of aluminum. What makes this machine special? Well, the M8 Cube is built specifically for high-speed precision work. Its spindle rotates at speeds up to 60,000 RPM. That's 1,000 revolutions every single second. The machine's compact workspace, measuring roughly 420 by 500 by 220 millimeters, might seem small, but it's perfectly designed for intricate aerospace components like this drone propeller mold. Watch how the cutting tool dances across the aluminum surface. The M8 Cube uses what's called adaptive toolpath technology, which means it automatically adjusts cutting speed and depth based on the material it encounters. This isn't just smart. It extends tool life and ensures consistent surface quality. The machine's linear motor drives provide acceleration forces up to 2G, allowing for those lightning-fast directional changes you're seeing. Notice the excellent surface finish being achieved. That's thanks to the machine's vacuum table system holding the workpiece absolutely rock solid, eliminating even the tiniest vibration. The integrated coolant system keeps both the cutting tool and aluminum at optimal temperature, preventing thermal expansion that could ruin precision tolerances measured in microns. This fiber mold will be used to create lightweight, ultra-strong composite propellers, a perfect marriage of old-school mold-making principles and cutting-edge automation. That's modern manufacturing at its finest, folks. If you've ever wondered how those massive cylindrical tanks, pressure vessels, or wind tower sections get their perfect curved shape, you're about to find out. This is the new Bremen Heisler-Walls plate rolling machine, and it represents over a century of German engineering excellence refined to near perfection. Bremen and Heisler merged their expertise to create what's arguably the most sophisticated plate rolling technology available today. This particular machine can handle steel plates up to 80 millimeters thick and 4 meters wide. That's over 3 inches thick and 13 feet across. Let's talk about how this beast works. You're looking at what's called a 4-roll configuration. See those cylindrical rollers? The bottom roll is the main drive, powered by hydraulic motors that can exert hundreds of tons of force. The 2 side rolls are positioned at precise angles, while the top roll applies downward pressure. Together, they gradually bend flat steel plate into perfectly circular or conical shapes. What's revolutionary about this new model is its CNC control system. The operator inputs the desired radius, and the machine automatically calculates the exact position for each roller, accounting for the material's thickness, grade, and even its yield strength. This eliminates the trial-and-error approach that old-timers like us remember from decades past. Watch how smoothly the plate feeds through. That's thanks to individual servo motor control on each roller, maintaining consistent pressure and speed. The machine can even perform pyramid rolling, pre-bending the plate edges first to eliminate flat spots, something that used to require separate equipment. The hydraulic clamping system you see holds the plate edge securely during the initial bite, preventing slippage that could create imperfections. Temperature sensors monitor the rollers continuously because even slight thermal expansion could affect tolerances. This technology is building everything from oil refinery components to the massive towers supporting modern wind turbines. It's heavy manufacturing that connects us to an industrial heritage stretching back generations, just executed with 21st century precision. Let's finish up with something that connects virtually every building and industrial facility you've ever worked in: pipe fittings. These stainless steel and carbon steel components might not look glamorous, but they're absolutely critical to modern infrastructure. The production process begins with quality raw material. For stainless steel fittings, typically 304 or 316 grade, the manufacturing starts with seamless or welded pipe stock. Carbon steel fittings usually come from grades like A234 WPB, selected for strength and weldability. The pipe section is heated to approximately 1800 degrees Fahrenheit in specialized induction furnaces. At this temperature, the steel becomes plastic enough to form without cracking. Hydraulic presses then shape the heated material into elbows, T's, reducers, and caps. After hot forming, fittings enter the critical heat treatment phase. For stainless steel, this means solution annealing, heating to about 950 degrees Fahrenheit, then rapidly cooling. This process dissolves carbides back into solution, maximizing corrosion resistance. Carbon steel fittings undergo normalizing, which refines grain structure and relieves forming stresses. Now observe the machining operations. End bevels must be cut to precise angles for proper welding. CNC lathes and milling machines create these features with repeatability that manual machining could never achieve. Thread cutting for threaded fittings requires proper thread form, pitch, and depth, standards established decades ago and maintained today. Surface finishing is next. Stainless fittings receive pickling and passivation treatments, removing surface contamination and forming a protective chromium oxide layer. Carbon steel fittings are often coated with black oxide, galvanizing, or specialized coatings depending on their application. Final inspection involves dimensional verification, pressure testing, and often radiographic examination. These fittings might end up in power plants, chemical facilities, or water systems. Failure simply isn't an option.